So gradient descent is an algorithm that allows us to find the lowest point in our cost graph. And that lowest point corresponds to two M and B values, which means that there's an M value and a B value that ensures very, very small distance between our predicted outputs and the real outputs, which is exactly what we want. We want a very accurate model. The question is, how does this algorithm work? So it's iterative, meaning we're repeating this until we feel like we're really, really close to a combination of M and B that minimizes our error. We start with some guesses of M and B, say M is 0, B is 0, and we keep changing M and B to reduce our cost, keep changing them, whether that's increasing them, decreasing them, playing around, but we're simultaneously changing M and B until we feel like we've really converged to that lowest point in our cost graph. So let's kind of visualize this a bit. So again, let's go back to that two-dimensional example where we only have some coefficient M and our cost. So we start at some M initial, right? We're trying to get to that lowest point in the graph. We don't know where it is, but we need to try to find it. We need to try to find the exact value of M. So what we'll do is we'll take the gradient, and the gradient is the direction of steepest descent. So positive gradient would give us the direction of greatest ascent, and the negative gradient would give us the direction of greatest descent. And we take a small incremental step in that direction, and we change our value of M initial. Then we take the gradient again and take a small step in that direction again, and then another small step and another small step and another small step until we get to that lowest point in our cost graph. And hooray, we've reached the value of M that minimizes the cost. Great. So I just want you to notice that we're taking smaller and smaller steps here. The question is, how does this happen in 3 dimensions? But first, let's go over to the formulation. How are we adjusting M? We're adjusting M by using the original value of M in the previous iteration and subtracting it by the learning rate multiplied by the gradient. The learning rate is simply the step size at the rate at which we are moving our M value, and the gradient is the direction of steepest descent. So we're multiplying the rate of movement by the direction of movement. So we're trying to move in that steepest descent direction at a very small rate. Now, why would we not want to move there very fast? If our learning rate was really high, this could lead to a phenomenon called overshooting, where we would be adjusting the value of our M so drastically that we wouldn't be able to find the minima. So it's important to keep a very small learning rate. Now, really, the gradient is a partial derivative of the cost function with respect to M. And I'm not going to go too much into this. So if you do want to find external resources about partial derivatives, gradients, I will leave that at the end of this video. So make sure to stick for that. But this is the actual formulation for a gradient. Now, this is a really cool visualization of what gradient descent might look like. We're slowly adjusting the line so that the distances are minimized between the points and our line, and we converge to that value of, in this case, parameter A, that coefficient, so that we can get to a line that's really perfect, a perfect fit to our data. So that's pretty cool. But now the question is, how can we do this in 3 dimensions? So now we just need to adjust M and B simultaneously. And the same formula holds true. So again, partial derivative with respect to b and with respect to m. And that's what this formulation looks like. Now, in the Pythonic implementation that you'll be tasked to do in this curriculum, it's not that hard. You just require some basic knowledge of NumPy and maybe a sheet of paper that has all of these equations listed so you remember the implementation. But it's important to understand how this works mathematically, because without the basic mathematical concepts involved in the algorithm, we won't really understand how it works. Now, here's a cool visualization. Again, we're simultaneously adjusting m and b values, and we generate this cool graph. We start at the top of the graph at some random we start at the top of the graph at some random initialization point, and we slowly but surely get to our minima, our lowest point in the graph, where some combination of m and b yields the lowest error. That's pretty cool. So now the question is, how is this done iteratively in Python? We set our m and b values to 0. We set our learning rate to 0.01, which is some arbitrary value that we've chosen that works really well. And then we iterate. So for some set of iterations, we say for iteration in range. And then we do three things. First, we compute the error so we can visualize the error over time on a graph or on a plot. Then we are computing the gradients for m and b, the direction of steepest descent for m and b, and then simultaneously adjusting m and b. Because if we only adjust one variable, we'll only see how the cost changes with respect to the variable we're adjusting. We need to adjust both of them at the same time. And that's how gradient descent works. If you're interested in learning a little bit more, further mastering gradient descent and more mathematical aspects of it, make sure to go to this QR code and you'll get some really cool resources that go a lot more in depth. But the goal of this video was just to introduce you to how gradient descent works and the basics of how to implement it. Now your job will be to implement linear regression from scratch in Python. There's a notebook attached to this module that will walk you through how to do it. Good luck.